Okay, in this podcast, I'm going to go over the problems from the acid-base test. And I'm going to go in this order. First, I'm going to start with FRQ. And both versions were the same, so I'm going to talk a little bit about question 1 again, do a recap of A and B, and then do C completely. And then I'm going to do all of question 4. And then I'm going to do these questions from version A and B, which are the pairs, in the following order. So if you have version A, I'm going to do 10, then 20 last. And if you have version B, I'm going to do 8, and then 18 last. Okay, so let's go ahead and get started. Alright, so let's go back to number 1. We had the percentage by weight of nitric acid in a sample of concentrated acid is to be determined. Okay, so initially we have a sample of NaOH solution, which was standardized by titration with a sample of, I'm going to call that KHP, which is a monoprotic acid often used as a primary standard. A sample of pure KHP weighing 1.518 grams was dissolved. Okay, and titrated with the NaOH. So the first thing we want to do is calculate the molarity of the NaOH. Okay, so this is a titration, and when we reach our equivalence point, we want the moles of acid to equal the moles of base, or really moles of H plus to equal the moles of OH minus. And in this case, because these are both monoprotic, this is monoprotic, this is monohydroxide, we can use moles of acid equal moles of base. Okay. If this was diprotic, we'd have to use twice this amount, right? Because we get 2 H's for every 1 OH. Alright, anyways. So we can figure out what our moles of acid is by taking 1.518 grams, I'm just going to say, of the acid, or I'll call it KHP, and using its molar mass, dividing it by its molar mass, which is 204.2, that was provided for us, and we get 0.007433 moles of acid. Okay, now that mole of acid is going to equal my moles of base, and we know that moles is equal to molarity times the volume in liters, right? And we're trying to find molarity, so the molarity of the base, which we're trying to find, times the volume in liters. Now we're given this in milliliters, 26.90, so in liters that's going to be 0.02690. And so to get B, molarity of B, it's simply going to be 0.00743 moles over 0.02690 liters. And this is going to give me a molarity of 0.2763 molar. And there should be 2763. And I want 4 sig figs. I have 4 sig figs here, and I have 4 sig figs here, so I should have 4 sig figs here. Alright. Second part of the problem says a 100 milliliter sample of the concentrated acid was diluted with water to a volume of 500 milliliters. Okay, and then 25 milliliters of the acid was titrated with the standardized sodium hydroxide solution that we prepared in part A, and the equivalence point was reached after 28.35 milliliters of base. Calculate molarity of the concentrated acid. And if you hear me drinking, I'm drinking my coffee because it's 4 a.m. Alright, we have 10 milliliters. I'm just going to kind of draw schematically what I have going on here. So I have 10 milliliters of nitric acid that I put in water, and I get 500 milliliters of HNO3 dilute. Okay. And then I take 25 milliliters. Let's do it here. I take 25 milliliters of that. Of the HNO3 dilute in here, right? And I titrate it with NaOH, and I know its molarity from the previous problem, right, which was 0.2763 molar, and I know its volume, right? It's given to me here, 28.35 milliliters. Okay. All right. So let's take a look. So first, what I want to do is figure out what my molarity of the dilute acid is. So I want to find the molarity of this, and I am given the molarity and the volume of this. Okay. So again, we have monoprotic and monohydroxide. So I can say molarity of my acid times the volume of my acid equals molarity of my base times the volume of my base. Alright, and I am trying to find molarity of my acid, so that's what I'm going to use. So my molarity of my acid is going to be molarity of my base, which is 0.27, and because 2763, because I'm using milliliters in both cases, and I can keep this in milliliters. Okay, and I've got 25 milliliters of the acid, and if I calculate that out, what I get is 0.3133 molar HNO3 dilute. Okay, but the question asks, what's the molarity of the concentrated acid? Alright, so this is my molarity of my dilute nitric acid. It's in 500 milliliters. Okay, what I want to know is what is my molarity of my I'm just going to call this concentrated acid. Okay, and I have milliliters in both, so I can stick with milliliters. So my molarity of my concentrated is going to equal my I'm using M1V1 equals M2V2, which I can rearrange. So my molarity of my concentrated is my molarity of my dilute times the volume of my dilute over the volume of my concentrated. So that is going to be 0.3133 molar times the volume of my dilute, which is 500 milliliters, over my volume of my concentrated, which was 10 milliliters. Milliliters will cancel out, and if I do that, I am going to get 15.67 molar. And let me see, 4 sig figs, 4 sig figs, 4 sig figs, so I want 4 sig figs. Okay, so that was part B. Now part C says the density of the concentrated nitric using the experiment has this many grams per milliliter. Determine the percent by weight of nitric acid in a sample of concentrated nitric acid. Okay, so in order to find the percent by weight, I'm going to have to get the grams of HNO3 that is present over the grams of basically HNO3 concentrated, right? Or the aqueous. Okay. So let's see, how can we find the grams of HNO3? So what I know is I have 10. If I go back to the previous problem, what I knew is I had 10 milliliters of HNO3, right? And I can use this density, right, what I know is there's 1,000 milliliters in 1 liter. Oops. I don't even need to do that. I can skip that step. Let me just erase it so we're not confused. Alright, so let me just get my pen back. Alright, and what I know... Okay, actually, I'm thinking of the wrong problem. So I have 10 milliliters of nitric acid, right? And I'm trying to figure out the grams of actual HNO3 that are in that. So I am going to use that. 1,000 milliliters is 1 liter, right? And I know the molarity. I know that the molarity of the concentrated acid was 15.67 moles, or molar. So 1 liter is 15.67 moles of acid, right? And I know that in 1 mole of acid, the molar mass is 63.02 grams of the acid. And if I multiply this out, I get 9.88 grams of the acid. And so I'm going to put that up here. Okay. And now I can find the mass of my solution. So again, I have 10 milliliters of, I'm just going to say, of the acid. And what I know is the density is 1.42 grams per 1 milliliter. So if I multiply this out, I get 14.2 grams. Okay, so I'm going to put that here, 14.2 grams. And I'm just going to take this, I multiply it times 100 to get this as a percent. And if we do that, we get 69.5% HNO3. Okay. Alright, here we are on question number 4. We have HF dissociates in water as represented by the equation below, gives us a Ka. We want to write the equilibrium constant for the dissociation of HF in water. Okay, so equilibrium expressions by now we should be pretty good at, right? That is simply, we write what our Ka is equal to, and we know it's 7.2 times 10 to the minus 4, so we might as well put that in there. And that equals the concentration of our products, H3O plus, times F minus, over our reactants, right? So I didn't use HF. Water is a liquid, so I don't include that. So that's my equilibrium expression. Okay, so we want to calculate the molar concentration of H3O plus in 0.4 molar HF. Okay, so this is a weak acid, and we know that because we're given the Ka. So we're going to need to use a Rice table. Okay, so what we have is, let's do RICE, and the reaction is HF. I can leave the water out. Gives me H3O plus and F minus, right? So initially I have 0.4 molar, and initially I have no hydronium and no fluoride ion. So I'm going to lose some amount and gain the same amount from a molar concentration standpoint of my two ions. So this is going to be 0.4x. This is going to be, 0.4 minus x. This is x, and this is x, right? So let's see. Alright, so my Ka, which is 7.2 times 10 to the minus 4, is equal to my, I'm using this formula up here, x squared over 0.4 minus x. Okay, so on the AP exam, there's never been a reason to keep the x. It's always been considered negligent, so we can and this is a -4, I'd say if it's less than a 3, you're probably going to have to use it, but to date there has never been a chance for the quadratic to be used on the AP exam. So I'm going to tell the readers that I know this is going to be neglected. So my x squared is going to be 7.2 times 10 to the -4 times my 0.4 molar. That's supposed to be an m. So take the square root of both sides and I get x is equal to 0.017. Now I got 2 sig figs, so I'm going to leave it at 2 sig figs molar, and that's the concentration, just want to remind myself, of H3O+. Alright, so here we're given a volume of 15 milliliters of 0.4 molar sodium hydroxide is added to 25 milliliters of 0.4 molar HF, right? And we're working off this equation of, let me see, HF, this was given to us, right? Plus OH minus gives us H2O plus F minus, right? So we want to know it says the volumes are additive, which is very useful to us. So this is a limiting reactant problem, right? So what I know is that for every 1 mole of this, I'm going to use 1 mole of this, get 1 mole of this, and get 1 mole of this, right? So first I have to figure out how much hydroxide gets used up, and then that will tell me how much HF gets used up, and that will allow me to figure out how much I have left based on what I started with minus what I used. Okay, so let's just take a look at it. So how much base I'm going to use is going to be, so my moles, I'm going to do my moles of base, right? It's going to be molarity of my base times my volume in liters of my base. And so that's going to be 0.40 molar times 15 milliliters. So that's going to be 0.006 moles. And this is limiting, right? I can tell because I've got fewer milliliters of that. They're the same molarity, but I've got more milliliters of the HF. Okay, so my moles of acid are going to be my molarity times my volume in liters of my acid, which is also going to be 0.40 molar, but in this case it's 25 milliliters. And if I multiply this out, this was 0.015, this is 0.025, I'm going to get 0.01 moles of my acid, right? This is my base, this is my acid, and I'm looking for a leftover HF. Okay, so if I take 0.01 moles of this, is my starting volume, or starting number of moles, I'm going to use whatever it took for OH, minus 0.006 moles to neutralize. I'm going to have 0.004 moles, and I want 2 sig figs, 0.40 moles of HF remaining. Okay. So let's take a look. Okay, so now we want the molar concentration of F minus in the solution. So if I think about this reaction, for one of these, I get one of these, right? Alright, so my concentration of F is going to be my moles of F over my volume in liters of F. So that's going to be, this is what's left over, right? So when I have 0.006 moles used, it's neutral, right? And I just have water, but this is remaining F, so I 0.00, I'm sorry, 0.00, okay, D says calculate the molar concentration of F minus in the solution. Okay, so I had F in OH minus, and they neutralized when I had 0.006 moles of each, right, and gave me, which should be the equivalent amount of F minus, right, because their mole ratio is 1 to 1. So if I want to calculate the concentration of F minus, it's going to be the moles of F minus over the volume in liters of the solution. So my moles of F minus is going to be the same moles that it took the reactants, and my volume is going to be the total volume, right? 15 milliliters plus 25 milliliters, which is 40, so it's 0.040 liters. So my molarity is 0.15 molar. Alright, so now I want to calculate the pH of the solution. So if we remember, so we've used, if we go back to our equation, we have used all of our OH, right? We have 0.004 molars of HF left, right, after things have been neutralized. And what I need to know is, in order to find the pH, I have to find the concentration of that this leftover acid produces of the H+. Okay? So I do know I can figure out my HF concentration, starting concentration, which would be, so my molarity of my HF is going to be the moles of HF over the liters of HF, right? So I knew I had 0.004 moles left, and I have the added volumes, which we said was 0.040 liters. And this comes out to be 0.1 molar. So now I can use that and set up the Rice table. So my RICE, so we're talking about, this case, HF. There's water, which I don't need to show, becoming H+, and F-. Now HF, we just said, was 0.10 molar. H+ and F, starting volumes are none. Actually, they're not none, because we already said we have this concentration of F- in the solution, so we can use that, right? So F is not 0. F is going to be, let's just get my pen back. Alright, so what I have here is 0.15 molar. Okay? So I'm going to lose some HF here. I'm going to gain equal amount here. Minus X. So my ending is 0.1 minus X. This is going to be X, and this is going to be 0.15 plus X. Alright. I'm going to extend my page a little bit. Let's go up a little bit. Okay. So now I can put it into the equilibrium expression, and I know my Ka. It was given to me. I figured it out earlier, right? Or it was given to me. And what I know is that's going to be the concentration of H+ times F- over my concentration of HF. So that's going to be X is H. F- is 0.15 times X. 0.15 minus X, I should say. Over 0.1 minus x. My bad. This is a product, so it's 0.15 plus x. Okay, so here we have to think what we're going to do with our x's. We got kind of a mess here. So what we know is HF is very weak, right? We know the Ka, let's bring that back, is 7.2 times 10 to the minus 4. We said that it's going to be insignificant, so we are going to neglect this. And we are going to neglect this. Okay? And so that will give us 0.15x over 0.1. Okay? And we're trying to solve for x. So 7.2 times 10 to the minus 4 equals 0.15x over 0.1. So this becomes 7.2 times 10. I'm just going to change my exponent to a negative 5 equals 0.15x. So my x, which is my H plus concentration, is going to be, let me see, 7.2 times 10 to the minus 5 divided by 0.15 is going to be 4.8 times 10 to the minus 4. So my pH is equal to the negative of the log of 4.8 times 10 to the minus 4. So that is going to be let me see, we've had two sig figs all along, so it's going to be 3.32. Alrighty. Okay, so here we are on what's question 10 on version A and question 8 on version B. We want to know the pH of a 0.1 molar H2S. Okay, so we're given two Kas, right, because this has got two hydrogens, so it's going to have two equilibrium constants. So taking off the first S gives us this Ka, and second hydrogen coming off gives us this. So one of the things that's really obvious, should be really obvious, is that my second dissociation constant is tiny, 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 tiny. Look at that, how small it is. It's going to be totally insignificant, so I don't have to worry about that, right? And it's nice that this is so small because I certainly can eliminate X when I do my Rice table, right? Because this is a weak acid, so I need a Rice table. So RICE, we just said, well, they told us it was H2S, gives us HS minus, and, oops, I'm still on H plus. I'm still thinking HF. Okay, so I'm starting here with 0.10 molar. No product. I lose some X. I gain the same amount of X for each of these. So this is 0.1 minus X. This is X. This is X. So my Ka is going to be my concentration of HS, my products, plus times H plus over H2S. And so I know my Ka is going to be 1 times 10 to the minus 7 is equal to HS, which is X, and my H plus is X, so that's X squared, over my concentration of my H2S, which is 0.10 minus X. And we just said this is so tiny we can certainly neglect this. So 1 times 10 to the minus 7 is equal to times 0.1. I'm just going to change the exponent by 1. That becomes 1 times 10 to the minus 8th. And you should know that that is going to be, that's equal to x squared, right? So when I take the square root, what you should recognize is that square root of 1 times 10 to the minus 8th, I just divide this by 2, right? If I'm talking about exponents, it's going to be 1 times 10 to the minus 4. Okay? Because 1 times 10 to the minus 4 if I'm squaring it times 1 times 10 to the minus 4, right? When I'm multiplying, I add my exponents. That's going to be 1 times 10 to the minus 8th. Okay, so this is a skill you need to have in order to answer questions on the portion of the exam that does not give you a calculator. And some of the answer-based problems are going to be in the part of the free response that doesn't use a calculator, and certainly there are questions that are going to be in the multiple choice that will not let you use a calculator. So this is my H plus concentration, right, which I'm looking for. So my pH is going to be the negative of the log of 1 times 10 to the minus 4. And you should recognize this without a calculator. This is going to be simply this number, right? That's the negative of the log. The log is negative 4, so the negative of the log is going to be pH equals 4.0, and I had those choices, so this is my answer. Alright, so at 60 degrees C, the kW for water is 1 times 10 to the minus 13. And the pH of a neutral solution at this temperature is, and we have these choices, okay. So, we can think about water going to H plus OH minus. We know that kW is Ka times Kb, right? And if I'm making the same amount of H plus and OH minus, my Ka and Kb are going to be the same. So if I want to know the pH, I need to find the Ka, right? So Ka is going to be Kw over Kb, and my Kw is 1 times 10 to the 1 times, whoops. So it's such a habit of writing 1 times 10 to the minus 14, but they gave us a different one, right? Because that 1 times 10 to the minus 14 only applies when I'm talking about 25 degrees. And we are not, whoops, I thought I had my eraser there. We are not at 25 degrees. We are at, come on, baby. Give me the eraser. Now I need my pen back. Alright, so you're probably already done with this, but let's just take a look real quick. So it's going to be 1.08 times 10 to the minus 13. Okay, over my Kb. But my Kb and my Ka are the same, so what I should say here is Kw is equal to Ka squared, right? So Ka squared is equal to 1.08 times 10 to the minus 13. So the square root of this is equal to the square root of this. So my Ka is going to be, now this is a multiple choice question, and it's a reasonable question to put on the multiple choice without a calculator, right? So let's think about this. So if I had, if my exponent is 13, right, that's going to be somewhere between, let's think about it, 1 times 10 to the minus 14 and 1 times 10 to the minus 12, right? So if I had 1 times 10 to the minus 14 and I was taking the square root of that, that's of course 1 times 10 to the minus 7. If I was taking the square root of 1 times 10 to the minus 12, it's going to be 1 times 10 to the minus 6. So shouldn't my answer be between these two? And there's only one number here that is, in fact, between these two. And it's going to be that one. Okay. Alright, so we're getting close to the end. Alright, so this problem, we have a 0.15 molar solution of the following salts, and which one's going to be basic, right? So remember we said that if we have a strong acid in a weak base, we're going to have a an acidic salt, right? And if we have a weak acid and a strong base, we're going to have a basic salt. Okay, so we need to think about which acids or bases made these. Alright, so this is going to be KOH, right, which is a strong base, and HCl, which is a strong acid, so that's going to come out neutral. I'm just going to put an equal sign. Sodium nitrate. Sodium came from the sodium hydroxide, which is a strong base. NO3 comes from nitric acid, which is a strong acid. So this is also going to be neutral. So ammonium came from ammonia, and that's a weak base. And my Cl must have come from HCl, which is a strong acid. So this is going to be acidic. Okay. Sodium must have come from sodium hydroxide, strong base. Cn must have come from HCN, which is going to be a weak acid. So because this is strong, this is weak, this is going to be basic. Okay, let's just check this one. K is going to come from KOH, which is a strong base. I is going to come from HI, which is a strong acid, so this is going to be neutral. So that leaves me with D. Okay, so let's take a look at this one. So we have, okay, so in this one we have the Kb of a weak acid, and we're given the Kb, and we want to know the Ka of its conjugate. Okay, so this is what we have. We have C3NH2 plus water is going to give us CH3NH3 plus, right? Picks up a proton, plus OH minus, right? Now, we know Kw equals Ka times Kb, and we can use this, so if we have a weak acid, and we can do this for its conjugate base, or if we have a weak base, we can use this for its conjugate acid, right? So that's really what we have here. So what I know is Kw is going to be Ka times Kb. I'm trying to find Ka, so Ka is Kw over Kb, and that's going to be 1 times 10 to the minus 14 over my Kb is going to be what I'm given, which is 4.2 times 10 to the minus 4. So here, again, we're probably going to have to do this without a calculator. So 1 divided by 4 is about 0.25. 14 minus 4 is 10. So that'd be times 10 to the minus 10, right? Which will be the same as 2.5 times 10 to the minus 11. And I only have one thing in that range, and this would be it. All right. All right, so we want to rank boric acid, formic acid, and hydrocyanic acid in the order of increasing acidity. And this is really just a test of whether or not you can do the mental math. Now you could do this without should be able to do this without a calculator, right? All right, so the larger my Ka, the more the acid dissociates, which means the stronger the acid is. This is definitely going to be my strongest. So it's really a question of how this compares to this. So you do what works for you, but you got to get really clear on how the logs work. So let's say I have 1 times 10 to the minus 9 and 1 times 10. I'm just going to put them on a scale. And 1 times 10 to the minus 11. So this is strong and this is weak, right? So I need to think about where 5.9 times 10 to the minus 10 falls. Okay, so it's going to be, it's more than 1 times 10 to the minus 10. So it's going to be getting closer to 1 times 10 to the minus 9. So it's 5.9 times 10 to the minus 10. Let's place it here, because it's getting closer to the negative 9 as this goes up from 1, right? Once it reaches 10, it becomes 1 times 10 to the minus 9. And so my 4.9 is further away from that 10 to get to the negative 9. So this is going to be 4.9, 10 to the minus 10. So this is going to be the weakest, right? So my 0.9 is going to be my weak. And then we have to not make the silly mistakes that I make sometimes. So this is greater than, right? So formic acid is my strong, so that leaves me with these two choices, but I want my weak to be hydrocyanic, so my answer is D. And we're done.